I mentioned before this idea of a logistic function, which is also called an S-shaped or sigmoid-shaped function. Sigmoid because sigma is the Greek letter S, and some sigmas long ago used to be drawn like we draw S's today. So here, it's a really handy function. The logistic function, this one is 1 over 1 plus e to the minus x. And if you're writing it in Excel or something all in one line, you have to write it this way. You really need those parentheses around the denominator, otherwise it's just going to do 1 divided by 1 and then add a decaying exponential. The logistic function, it sounds a lot like the word logarithm, but they're very, very different functions. This doesn't even use the word logarithm. It doesn't use the log function, and it behaves very differently. So this function here, for if x is 0, then e of the 0 is 1, and you get 1 over 2. So at x equals 0, it crosses through 0.5. For really large x, you get e to the negative large, which is very tiny. So you get 1 over 1 plus tiny, which is basically 1, so you're out here. If x is very negative, then e to the negative x is e to a large positive number, which is huge. Add 1 to that, it's still huge. Divide 1 by a huge number, you get a number near 0. So that's how it's behaving over here. So it's a smooth transition from a horizontal asymptote near 0 to a horizontal asymptote near 1. Logistic functions are used in applied probability and statistics. They're used in machine learning stuff for the activation of a neuron. Don't worry if you don't know what that is. Basically, they take a number from minus infinity to plus infinity and make it fit into the range 0 to 1. So it's a way to keep stuff from exceeding some limit. It's often a useful thing in engineering. So that's our main logistic function, and it goes through that point, and by the time it hits 2, it's kind of near 90%, and around negative 2, it's near like negative 5, negative 10%. At negative 2, it's at 5 or 10% of its ultimate value. But not everything in the world does this, right? Not everything is centered at 0. Sometimes we need it to be taller. Sometimes we need it to be centered over here, increase faster, increase slower. So we can make it do what we need it to do by putting parameters on it like this. And I've just chosen A, B, C, and D just alphabetically. We probably could have chosen them based on what they actually do. So take a second, think, for A, B, C, and D here, what's a vertical shift, what's a horizontal shift, what's a vertical scale, what's a horizontal scale? So write down your answers. Okay, welcome back from pausing. So A here is a vertical shift, or some people call it a vertical translation. B is a vertical scaling. It makes it taller or shorter. Or some people call it a dilation. It's a lot like a amplitude for a sine wave. What is C? C is multiplying x. We're used to a slope multiplying x, and slopes change how steep things are. And here, you can think of that as either a vertical scaling or horizontal scaling. But here, since it's inside the nonlinear part, we're going to say that is a horizontal scaling. Or you could say a horizontal dilation. And this one is affecting which x kind of acts like 0. Like if d is 10, then when x is 10, you get a 0 here. So x equals 10 kind of acts like 0. So this is a horizontal shift. Horizontal scaling is kind of like frequency. And horizontal shift is kind of like phase shift. So that's how these various parameters relate to shifting and scaling sine waves. So now we're going to switch to Desmos and show this in action. All right, here we are in Desmos. We'll type our logistic function. We could just call it L of x, but we usually use that for tangent lines, so I'm going to give it a subscript of logistics so we can kind of read it. And take a sec if you try to remember what it was. Ready? 1 over 1 plus e to the negative x. Negative x, there we go. And then our shifted and scaled version of it was a plus b times logistic of c times x minus d, and we want sliders for all of those things. We'll let ourselves see that. All right, so our blue curve here, now I've been using red and blue for like original and derivative, but these are not original and derivative, so I'm just going to change colors entirely. How about orange and black? And we even put the orange in kind of dotted because it's not the main function we're concerned with. We're concerned with shifting and scaling and stuff. All right. Whoa, there we go. Control Z works as undo in Desmos. That's handy sometimes. So here's our original function, and like we said, it's going through 0.5. Like here's y equals 1, here's y equals 2. So it goes through 0.5 at x equals 0. And that, if you look at what I have to do to this to get that function, that's setting a equal to 0, having a 0 vertical shift. B of 1, that makes sense because we're just multiplying by 1. C of 1, because we just have x in there. So if C is 1, then I just multiply x by 1 and it goes there. And then D of 0, because I don't have a subtraction term originally, so I would just put a 0 there. So those are the kind of default settings to get the same curve that we started with. And then what's going to happen if I change A? So I get that vertical shift, like I said. What's going to happen if I change B? Take a sec to think about it before I do it. Ready? Make stuff taller. And I can even make B negative, and that flips the whole curve upside down. If I didn't want the result to go into negative territory, I could shift stuff up. So it starts at a horizontal asymptote near 1, and then goes down toward a horizontal asymptote of 0. Let's shift A back to 0, and B back to 1. Doesn't really matter. What about C? Do you remember what C did in this formula? Well, it's multiplying x, so it's kind of like a slope. So the larger I make C, the more strongly sloped this gets. And the less I make C less than 1, it gets not as strongly sloped as the original function. What's going to happen if I push C into negative territory? Oh, then we get a negative slope. That's kind of handy. Let's bring this back here. And then D is the horizontal shift. Let's show that. So that's subtracting directly from x. So the lower I make D, the sooner this peaks up. That's moving the center point to the left, or I can move the center point to the right. So that is fun with shifting and scaling and logistics. Here I've written it using a kind of main shape function, and then another function that uses the main shape function. So that's handy, but sometimes in Excel, for example, you can't define your own user-based function. Like, you can't define this own function. You have to do it all in one line. So if you need to do that, you can say g of x equals a plus b times 1 over 1 plus e to the. So this is our main logistic function. I'm doing the vertical shifting, vertical scaling. But then I have a negative, but then instead of x, I'm going to write in all this stuff. So I'd say c times, whoop, I need this to be in parentheses, c times x minus d. I actually don't need this parentheses around it. I just had to do that to tell Desmos to not let the next thing be out of the exponent. So g here should be acting exactly the same as f. So let's try that. Like, let's make it steeper. Yep, that seems to not be giving me two separate curves. So sometimes it's good to think of, I have a main function and then a shifted and scaled version of it. Sometimes it's good to think of it all as one function, because then you can enter that into Excel, for example.